Hopefully, as you were working on Desmos, you started to recognize some of those transformations that you learned in Algebra 2 and also maybe Algebra 3. One big difference, if you went to the textbook to help you fill out any of the Desmos activities, is our pre-calculus textbook shows all the transformations in function notation with the letter C, so it uses the same letter. And then in Algebra 2, and I'm not sure about Algebra 3, they use 3 letters for parameters A, H, and K. So oftentimes in Algebra 2 we review, okay, what does A do, what does H do, what does K do? Here we just call it the same value C. It's just transformations and piecewise functions.
What sections?
1, 7, and 1, 6. Transformations and function notations. The first set of transformations we're going to talk about are rigid transformations. Rigid means we're not going to change the size or the shape of the graph. We're only changing its location or its orientation in the coordinate plane. So it stays rigid. It doesn't move other than to change location or change orientation. Horizontal shifts and vertical shifts, you might have called those translations in Algebra 2 and also geometry. Does anybody remember, like, what's the big difference between horizontal and vertical shifts?
Where they're located.
And what do you mean by where they're located, Mason?
Like horizontal or in parentheses for going outside.
Yeah, it's where you put the number, right? When you put the number inside the parentheses, then it's inside the parentheses with the x variable, and so it's changing with the x, which would be left and right. Whereas when you add or subtract something on the outside of the parentheses, then you're really adding or subtracting to the y value, which would be changing the up and the down of your function. Good. So horizontal shifts on your Desmos activities, you can use other letters. Like if you were going off of your Algebra 2 knowledge, you might have used H instead of C. If you looked in the textbook, you might have chosen C. Okay. But the two horizontal shifts are f of x minus c and f of x plus c. And f of x minus c moves us to the right. F of x plus c moves us to the left. I always tell students, when you put something in the parentheses with x, it does the opposite of what you think it will do. So like normally negatives would go left, but here we actually go right. Then vertical shifts, like Mason said, are going to be outside the parentheses. So we're just going to have our f of x and then add and subtract c behind it. Remember to think about, in that particular case, f of x is really just a fancy way for us to write y. So we're saying take the y value, add c to it. It moves the y value up, c units. Take the y value, subtract c. It moves the y value down c units. Okay, so those are our horizontal and our vertical shifts or translations. Another set of rigid transformations are going to be the reflections. And you can reflect things over any line, but in functions, when we talk about that algebraically, we're really concentrated on reflecting over the x-axis, reflecting in the y-axis. What causes reflections in function notation? The negatives, right, are going to be part of our reflections. And we'll have the same issue with reflections that we had with vertical and horizontal shifts. Is it inside? Is it outside? Now, I always like to encourage people to think about this visually. And so I'm going to put a point A here in quadrant 1. And if I were to reflect A in the x-axis, then it would reflect down, and my new point A prime would show up in quadrant 4. So you can see that if you compare those 2 points, I'm going the same distance to the right. Really, it's my y that changes and becomes negative. So when you want to reflect something in the x-axis, you want to change the y's to their negative or their opposites. Okay? So a reflection in the x-axis should be negative f of x. because remember f of x is really just y. And a reflection in the y-axis, if we go back to this original point A, we'd reflect it over the y-axis. I've got a new point A prime. We can see this time I've changed the direction of my x, so I'm going the opposite x. I want to have the same y value, so this is where I put the negative inside with x. Now, you'll have to be careful on some functions. Like a good example of a function where you might have some issue would be like the quadratic function. So its parent function is f of x equals x squared. If you were to reflect it in the x-axis, you would just put a negative in the front, and then the parabola would open down. And so that would be a reflection in the x-axis. Versus a reflection in the y-axis, you would want to put the negative in front of just the x. If you want it just in front of x, you'll have to use a set of parentheses. Okay, so that would look like f of x equals parentheses negative x squared. And then if you were to simplify that, it would just come out to be x squared, the original parent function. And that should make sense because if you think about reflecting the parent quadratic function over the y-axis, you wouldn't tell the difference. Okay, it would be the same. Okay. So be careful with some of them. Like when you put this negative in front of the x squared and you leave it negative, then you're making it a y. You're changing the y to a negative, so you're making a reflection in the x. If you want it to be a reflection in the y, you've got to use parentheses on that one. Okay. So be careful. The next set of transformations are going to be your non-rigid transformations. Those are basically our stretches and our shrinks. I'm going to give myself a little bit more space to write here. To stretch and shrink things, I often think back to just like basic geometry class, and I know it's been a while since you guys have been in geometry, but in geometry you talked about something called a scale factor. When you wanted to make things larger or smaller, you multiplied them by a scale factor. It's the same idea in a graph. We want to multiply either our x-coordinate or our y-coordinate by a factor to make it stretch or shrink. If you're doing a vertical stretch or shrink, think again logically about which coordinate you would want to multiply. To stretch it vertically or shrink it vertically, you'd want to multiply it by x or y. Y, okay, because it's going to do the vertical. So that's our c times f of x. Whereas a horizontal stretch or shrink is going to be f of c times x inside, so that you multiply it by x. If you want to stretch something out horizontally or you want to shrink it horizontally, you're going to multiply inside, so that you're multiplying the x variable, not the y. Now, the Desmos reflection questions asked you, what are the values of C which produce vertical stretch? Did anybody get that or remember? Whenever C is greater than 1, and I'm going to include absolute values there, so I'm going to say when the absolute value of C is greater than 1, we have vertical stretch. The only reason I'm saying absolute value there is because if it were a negative in front, the negative would be responsible for a reflection in the x-axis. The absolute value of that number is actually responsible for our stretch or shrink. And so when we want to shrink it, we'll have the absolute value of C is somewhere in between 0 and 1, a fraction, a decimal, less than 1. Again, I'm not really including any negative numbers with stretch or shrink because the negative would actually be a reflection. And then horizontal, they switch. It goes back to that whole idea that anything you do inside the parentheses with x is kind of the opposite of what you think it will be. Okay, so you'll have horizontal stretch when the absolute value of C is between 0 and 1. We will have horizontal shrink when the absolute value of C is greater than 1. For horizontal stretch and shrinks, if you want to apply those like to your table of values, your x coordinates, you always multiply by the reciprocal. So where C might look like 3 in a horizontal shrink, you're really multiplying all your x's by a factor of 1/3. Hopefully you came up with similar conclusions on the Desmos activity, either on your own, what you knew from Algebra 2, or if you checked the pre-calculus textbook. Here's a couple of quick examples of what you're going to be asked to do on the assignment that you're going to work on here shortly. If I give you a function, so here I'm giving you g of x equals 7 minus x squared. I want you to do 4 things. A, I want you to describe the parent function. B, I want you to describe transformations. C, I want you to sketch the graph. And D, we want to use function notation to write g in terms of f. Of those 4 things, A, B, and C, you probably spend a lot of time with in Algebra 2. Identifying parent functions, identifying transformations, graphing the transformed functions. We're spending a little bit more time focusing on like that, what that function notation looks like. So I'd like you to have a quick chat with your small groups. What is the parent function? What are the transformations? Can you come to consensus? I'll call on you momentarily. So have a quick chat with your group for g of x equals 7 minus x squared. Do part A and part B. What is the parent function? What are the transformations?
Negative x. So if you like switch the area to plus 7.
Lily, can you tell us the parent function? Great. F of x equals x squared. Some people may also just name the function family quadratic. That would also be acceptable. Ethan, can you give us a transformation?
Moved up 7.
Up 7. And Lexi, do you have another transformation? Reflect in x-axis. Mitch, do you agree? Dylan, do you agree? Anybody disagree? Good. Okay. I would agree with those. Okay. We're going to sketch the graph. Okay. To sketch the graph here, I would think about the parent function of the quadratic, which I know to be a parabola with vertex at 0, 0. I'm going to go ahead and in my head just reflect it in the x-axis. So now it's a parabola that opens down with a vertex at 0, 0. And then I'm going to shift it up 7 units. So my vertex is now at 0, 7. So to sketch a graph, I'm going to go up 7 units. And since there's no stretch or shrink involved, I don't have to multiply my x or my y by any factor, scale factor. I can just go ahead and keep sort of the same rates of change that the parent graph would have. So I know in the parent graph, if I go x equals 1, I'm at positive 1. Here I would go down 1 over 1 to keep that same rate of change, and I would do that on both sides. So I have on the parent graph 1, 1, and negative 1, 1. And then I could think about the next rate of change is if I go over 2, then I would go up 4. Well, now I would go over 2 and down 4. Oop, I don't want to go over 2. Doesn't look like much of a parabola there. I could do that on both sides, and that gives me a nice parabola. Okay. Make sure you feel comfortable with like the way that the parent function works. A simple table of values would help you with that. The last piece of this is writing the function notation, and this is where part A comes in really handy, and then also thinking about our Desmos activity. So Lily gave us f of x equals x squared. If we want to write in function notation using transformations, we can now ignore the x squared and focus just on f of x, and then we'll apply the transformations that we got that are up 7 and reflect in the x-axis. So I would take my f of x, to reflect it in the x-axis I would have a negative in front of the f of x, and to move it up 7 I would have a plus 7 behind it. Now last year in Algebra 2 you probably encountered some issues where like the order of your transformation mattered. So in this case, because we have positive 7, we must have reflected before we did our vertical translation. Okay. Because if you do your vertical translation and then reflect the graph over the x-axis, then you'd actually be at negative 7 for your vertex. Any questions there? Okay, one more quick example. I'm going to put it up and I'll just give you some time to come up with your answer. So take a minute to look that over and decide what your answer may be. You're being asked to identify the parent function and the transformations, and then also write the equation. So I'll give you a couple minutes to do that, then I'll show you my answer. Something like this. Piecewise functions are two or more equations over a specified domain. Basically, it's a function made up of pieces of different functions. And the specified domain is when you say, use this function for this part of the graph, and then use another function for a different part of the graph. Okay. A piecewise function is going to look something like this, f of x equals, and then usually it has a bracket connecting. You can have more than two equations. You can have upwards of 5 or 6, depending on what you're looking at there. And it's going to give you different functions. So I have the functions 1 minus x squared and x minus 6. But behind each of the functions, it tells me for what specified domain I actually use that particular function. So that very first function, 1 minus x squared, I only use that when x is less than 1. So for me, when I'm graphing that piecewise function, I'm going to make a small table of values for x's that are less than 1 and find out their y values, plot those points, and get a picture of my graph. What are some values that are less than 1? 0, maybe -1. And something to note, I'm also going to include 1, even though it says x's are less than 1, because 0.99 should be used with this function. So I really need to figure out what this 1 is. It's going to serve as an open circle on my graph, and it's going to be kind of like the boundary of that particular function. Okay. So then I just plug in those x's. 1 minus -1 squared is 1 minus 1 or 0. 1 minus 0 squared is 1 minus 0 or 1. And 1 minus 1 squared is 1 minus 1 or 0. And I can graph those points. -1, 0, 0, 1, 1, 0 is going to be an open circle. Because it doesn't have or equals to, that's not part of the graph, but it serves as a boundary. Okay. And then I see that that's quadratic. It should be a parabola that opens down. If I feel like I have enough points to get a good picture of that graph, I can graph it. If I want more points, I could put in -2 and -3 and continue to evaluate. So on the left side of my graph, I've got part of a parabola. On the right side of my graph, I just need to figure out some more points. I'm going to use x and x minus 6. And this boundary is for x is greater than or equal to 1. So I can include 1 in the table officially. And it's going to give me a closed circle now. And then I just plug those numbers in. I'll get -5, 2 minus 6 is -4, 3 minus 6 is -3. And I can plot those points separately. So 1, 2, 3, 4, 5. 1, -5, 2, -4, 3, -3. That's a linear function. It's going to be a line. So a piecewise function is pieces of different functions on the same graph. Any questions? Yes?
Can we call it the Frankenstein function?
The Frankenstein function. Sure, as long as you remember piecewise.